Hello and welcome to episode 4 of Astromagnet. I'm Arush Ramadurai,
And I'm Ishan Chakrabarti.
and today we're excited to be talking to Irwin Shapiro, Timken University Professor of Astronomy at Harvard University.
By the way, it's just university professor. It's not university professor of astronomy.
Okay.
Okay.
Welcome to the podcast. So when did you first get interested in astronomy? Why are you interested in astronomy?
Well, first of all, I didn't become an astronomer. I was interested in astronomy as a kid, but not with any idea that I'd become an astronomer at any point in my life. But as most kids, I was interested in what was up in the sky. What age I was exactly, I can't say. But I started reading about 10 or 11. I started reading all the books I could in the local library on science, and many of them were astronomy, popular books by James Jeans, for example, who was an English astronomer who wrote for the public. Some of what he wrote was for the public, and I gobbled it up. And I built my own telescope, which was the first telescope I'd ever seen. It was the one I built. It was during the Second World War, and you couldn't get metal. So I made a tube for my telescope out of wood, a 12-sided tube, which required a lot of intricate woodwork to make it all fit together. 12, you had to plane the two sides of each piece of wood to make an approximation to a circle. Anyway, I did that. That was at the age of 15. I ground my own mirror and stuff like that. It was a 6-inch telescope. I still have it. Not that I use it. Not that I ever used it all that much, but it was fun making it.
Can you talk a little bit about the education you received for your career?
Certainly. I went to a local elementary school. First of all, I grew up in New York City. I went to a local elementary school, which was just 2 blocks from my house, and I walked there, of course. And then the high school, New York City had 3 special science high schools. One Brooklyn Technical High School, one Stuyvesant High School, and one Bronx High School of Science. To go to the Bronx High School of Science, which was then considered the most prestigious, was from where I lived in New York, which was the South Shore of Long Island, Far Rockaway, was 2.5 hours each way. Only one person from Far Rockaway tried to go to Bronx High School of Science and lasted 1 term before giving up. Commuting 5 hours a day to high school is a bit much. For Stuyvesant High School, it was only 1 hour and 3/4 each way. And then the third school, Brooklyn Tech, from where I lived, was only 1 hour and a little more than 1 hour each way. So I went to Brooklyn Tech. It was the biggest of the 3 schools. And I remember my first day there, I felt totally lost. There were 6,500 kids in the school, which was enormous compared to my little elementary school. And there were all these kids walking up and down the hall. I felt like an absolutely little pea. But that all disappeared the second day, and thereafter, I felt perfectly at home. And I had what I consider the best education experience of my life. It was mainly due to my fellow students rather than to the teachers, because the good science teachers were off on war work. This was during the Second World War that I went to high school. So they were left with people teaching out of license, and I figured soon, wasn't long before I figured I knew more than the teachers, but that's another story. But the other students were all interested in science, and that was to me very important and very educational. And then Brooklyn Tech at that time was an all-boys school, no girls. And by the end of high school, I was tired of an all-boys school. I wanted to go to a school with girls. My father sent out for an application to MIT. I wasn't interested. Harvard, I wasn't interested in because I didn't know about Radcliffe. I wanted to go to Cornell. Cornell University at that time was, and still is, was co-ed. But what I didn't know until I got there was that there were 6 boys for every girl. And half the boys were old enough to be my father because they were returning veterans from the Second World War going to college. So my social life at Cornell was essentially nil, but it was a good time anyway. I played ping pong. I was a good ping pong player. I played on the high school. I was number 1 in the high school team, number 1 in my college team, and so forth. But be that as it may, then after 3 years, I wanted to avoid getting into the Korean War, which was in progress at that time. And so just starting. And so I graduated from college in 3 years and went directly to graduate school at Harvard in physics and kept out of the Army. Then when it came time for a postdoc, I decided to work at Lincoln Laboratory because they were still drafting people and I was not interested in being drafted. So I went to Lincoln Laboratory at MIT, where after 2 weeks, they sent after my being there 2 weeks, the assistant director of the laboratory accompanied me to my draft board and appealed to them on how essential I was to the defense of our country by working at Lincoln Laboratory. And so from then on at Lincoln Laboratory, I was called Indispensable Irwin as a joke, because obviously after 2 weeks, I was not exactly indispensable. And I stayed there for a while. Then in the mid-1960s, I got offers to be a professor at MIT, and I took the one from the Earth and Planetary Sciences department, and the one from the physics department I took also, but as a secondary affiliation, mainly because I liked the then department chair in Earth and Planetary Science, and I didn't really trust the department chair in physics. But that was a long time ago. At MIT, as opposed to Harvard, the chairs didn't change that often. People were chairs for the order of 10 years or so. So then I built up a research group at MIT. I'm not talking about any of my research projects, just giving you the sort of the outline of my career, independent of any research I did. And I built up a group of about 25. At the most, I had 12 graduate students at once and postdocs and a secretary and stuff like that. I grew about 25 all told at MIT. And then I got an offer from Harvard to be the director of the Center for Astrophysics, the Harvard Smithsonian Center for Astrophysics, which at that time had about 250 or so people. I wondered, could I really go from directing a group of 25, which seemed to me to keep my hands full, to going to a place which had 250 people. And in the end, I decided I'd do it, mainly because I thought it would give me a good platform to do something in pre-college science education. Why was I interested in that? Because in that time, my daughter was taking high school chemistry, and I was horrified. She had a book about 2 inches or so thick. She didn't even know what a wave was, and they were talking about molecular orbitals in the book. And it was clear to me that this was crazy. This is not the way to teach science. So I thought I'd be able to do something in high school science, pre-college science, by being the head of the Harvard Smithsonian Center. That turned out to be an interesting thought, but in the end, not as nearly so successful as I intended, and largely because of the stranglehold that book companies have on the textbooks in high school science. That's another long story in itself, which I will skip. but it was not a good influence. It was very hard to deal with. So I consider that I had only very limited success in science education. And then I was director there for 21 and a half years. I worked, I would say, on average, 100 hours a week. It was a completely time-dominating job, which I took very seriously. I built up the place to almost 1,000 people all told. I built scientific facilities. That is, I didn't build them with my bare hands. I got them started. I raised the money for them, and they're now still functioning frontline facilities. And I guess that brings me now to where I am. I'm 92 years old. Well, it will be Sunday. I'm exaggerating. It's only Saturday. Tomorrow I'll be 92 years old. I'm still, as you can see, somewhat in possession of my mental faculties, and physically I don't have any aches and pains. I still play tennis, but I must admit I only play doubles now. But I play. I played as recently as Thursday. I got a clean ace. I don't know if any of you know anything, either of you knows anything about tennis, but ace is a hard thing to do. You serve and the other person doesn't get their racket on the ball. That's an ace. Anyway, so I'm still able to play tennis reasonably well. I should retire someday, I suppose, but I have no incentive. Okay, so now you can ask me other questions. That gives you my whole life in a nutshell, except for my personal life, where I met my wife 62 years ago last Wednesday, and we're still together very nicely. We have two children, a boy and a girl, who my son, the older, has two children, a girl and a boy, and my daughter has three children, three boys. So I have 5 grandchildren, if you've kept score. And one of them is in graduate school, 2 are in college, and the other one is in high school, and the other is in what they don't call it junior high school, they call it middle school now. So that's sort of a snapshot of my personal life.
So you've had a very long career.
I'll say this. I hold the record by far for the longest time between teaching one's first class at Harvard and teaching the most recent class. You know how many years that is?
I'm going to guess more than 50.
And you, Ishan, you want to guess?
I think I read that you started like sometime in the 80s. I don't really remember what exactly the date was. So I'll also guess maybe around like somewhere like over 40 years. Yeah.
Well, you're both wrong. The first class I taught at Harvard was my first term as a graduate student, where a professor whom I hardly knew said he wanted to close up his summer home in New Hampshire. Would I teach his graduate course in mathematical physics? So of course I said yes. And that was October 10th, my birthday, 1950. So that was my first course taught at Harvard. And my most recent one was this past spring, so over 70 years. So I hold the record by far. No one comes anywhere near that span of time between first and last teaching at Harvard. All right, so enough of that 20 questions business.
Wow.
Okay, so what questions would you like to ask on?
Yeah, we were wondering if you had any particular courses or research experiences like in your career that you feel were important to your development as a physicist.
Important to my development as a physicist. Oh. I don't know that I've developed that much as a physicist, but I've had a lot of fun research projects. the first one, which I'm curious as to how you even found out about Project Westford. How did you even find out about that?
We were during our research, we came across like an interview from last year where you talked about it a little. Yeah, and it looked very interesting.
Oh, that was my first real taste of politics, as well as doing some reasonable research. That was in the beginning of the space age, when someone at Lincoln Laboratory had the idea. Lincoln Laboratory, by the way, is run by or funded by the Air Force to do research that's of relevance to the Air Force. And one of the things that is very important is communications. And the idea of Project Westford was to create an artificial ionosphere, if you will, that you could use to communicate by bouncing radio signals off it from one part of the world and be received at another part. And the beauty of the idea was that you couldn't jam this whole artificial ionosphere. So no opponent could get rid of it in any obvious way. So you had a jam-proof, secure communications medium set up that would be reliable in wartime and so forth. So that idea. Say again, I didn't hear.
Oh, I don't think anyone was talking. It was just some feedback on Arush's end. Yeah. So go ahead. Yeah.
Okay. So this became a very politically charged project, because the astronomers felt that it was going to put them out of business. Well, let me tell you what the idea was. The idea was to put in orbit 450 million copper dipoles, each about an inch or so long. So they'd be tuned to the frequency at X-band. And the idea was you'd put up a spinning canister made up of only these dipoles, and they were suffused with naphthalene, and they would essentially not boil off, but the naphthalene would be evaporated by sunlight, and these canister would be spinning, so the dipoles would come off individually from this canister, and then they'd spread out because of differential velocity of coming off. They'd spread out over time, took about 40 days or so, to form a belt around the Earth. Now, one of the really big problems was, could we keep that of finite length, the time that these would be in orbit? They would be in orbit at roughly 4,000 kilometers, something like that. So normal air drag would take forever to bring them down. But what I realized, what I figured out, was that there were solar resonances that could, with sunlight pressure, because the area to mass ratio of these dipoles was so high, they were influenced by solar radiation pressure much more than the normal satellite. And what I realized was there's certain orbits you could put the dipoles in where the sunlight pressure would monotonically cause the eccentricity of the orbit to increase until the perigee of the orbit was low enough to be sucked up by the Earth's atmosphere and bring down the dipoles. In fact, I predicted the day they would come down, most of them would come down, and it was later shown that they came down as well as they could be measured at the day that I predicted. That's another long story, but the point is, astronomers got very up in arms all over the world because this was going to ruin astronomy, because the dipoles would be interfering with the light from stars and whatnot beyond the Earth, and you wouldn't be able to do astronomy. First of all, that was totally wrong, certainly as far as his first experiment was concerned. But I even got a call from then famous astronomer, he's now no longer living, the name of Alan Sandage. I don't know if either of you have heard of Alan Sandage. He was a very famous astronomer from Caltech. And he called me up at my house. Well, he reached me at my house. And he told me that this whole idea to put up this belt for artificial ionosphere for radio communications unjammable, that this was all a plot of the East Coast astronomers to put the West Coast astronomers out of business. Because optical astronomy was centered on the West Coast, mainly with Palomar 200-inch telescope you've probably heard of, south of Pasadena, that this was a plot of the East Coast astronomers to get rid of the West Coast astronomers by putting them out of business. And then the East Coast astronomers would launch space telescopes above our belt and take back the leadership of optical astronomy. Such paranoia, I couldn't believe, but I swear that's what happened. Anyway, I could tell you lots of stories. I'll just tell you two. One, I was in England on I don't know how many of you know London. They have tubes, they call them tubes instead of subways. And I was on a tube and I was standing because all the seats were taken. And I looked down, the person sitting in front of where I was standing was reading a book on matrices. I don't know whether you know what matrices are, but anyway, it's not often you're riding on a subway and you see someone reading a book on matrices. So I started talking to him. So he continued to talk to me and he wanted to know what I did. So I was very vague and he kept pinning me down ever more precisely until finally I told him I was working on this project, this dipole project. And he was furious. How could I work on such a terrible project? He even got off at my stop on the tube to continue the argument as to why I should immediately stop working on that terrible project. And then the other is that someone also from England, but having nothing to do with my subway ride, let it be known to his superiors that the dipoles would not come out of orbit due to radiation pressure, as I had calculated via this resonance, that they would, the resonance would wear out, if you will, rather fast, and they wouldn't come anywhere near to coming out of orbit as predicted. So in those days, intercontinental telephone calls were not exactly trivial. There were big deals in those days. And this was the early 1960s. But I was set up with a call to this guy in England to try and find out what his objections were based on. So it didn't take me more than 3 minutes, I think, to figure out what mistake he made. He made the assumption that the orbital inclination of the dipoles would not change. That was a common assumption for satellites, which was a reasonable assumption in most cases, but not for the radiation pressure resonance that I had discovered. And so I pointed out to him, that's an assumption that's completely wrong here and that ruins the resonance. And if you take into account the actual change in inclination, you'll find out I'm right. So anyway, we hung up, and I think it was a day or so later, he had to admit through channels that he was wrong and I was right, and the project was able to proceed. I was even mentioned in the United Nations, my calculations. But I don't know if any of you have ever heard of Adlai Stevenson. He ran for the president of the US and against Eisenhower and lost both times. But anyway, he mentioned my results, which is pretty heady stuff for a guy who was only 30 years old. Anyway, so as a result, the project was able to go ahead and the dipoles orbited. But unfortunately, the release of the canister was delayed because this was launched on an Air Force satellite, which had a different primary mission. and we were just a secondary payload, and we weren't able to be released until later in the orbit than originally planned. So the orientation of the dipoles was not to have this canister perpendicular to the rays of the sun, but at an angle, so that many of the dipoles did not come off individually, but came off in clumps, which had, of course, much lower area to mass ratio than the individual dipoles. So there's still clumps up there from this launch, but all the individual dipoles followed the orbits that I calculated. Anyway, in the end, after this, active satellites became mature and reliable enough that there was no longer any need for an artificial ionosphere. So there wasn't a follow-on operational system. It was just a test. So that was my first taste of international politics and my first introduction to a real problem. And the main thing that came out of it, from my point of view, was this discovery of these radiation pressure resonances and the following of the orbits that showed the resonance in action was really neat. I could go on, but I won't. That gives you somewhat of a flavor of my experience in Project Westford.
So you're most well known for the Shapiro time delay effect. So we were just wondering if you could talk a little bit about that.
So in 1962, radar astronomy was just getting off the ground. Radar astronomy is sending radar signals to celestial objects, in particular planets, the moon and planets. And I attended a lecture at MIT where the person was talking about his laboratory determinations of the speed of light. And he casually mentioned at one point that the speed of light depends on the gravitational field in which the light is passing. And that caught my ear because I had always thought the speed of light was c, regardless of who measured it or where. That was what I had remembered from taking a course 12 years earlier in relativity. And so I looked up in a relativity book to check on what the heck he was talking about. And I discovered that was true. And I realized that, hey, that has never been measured. I could perhaps measure it with a radar signal that went by the sun. And so I set about calculating. I'd not had anything to do with relativity since I had taken this course a dozen years ago as a first-year graduate student. And so it was nothing to do with relativity in between. But I was able to fairly easily, just because I was facile at that sort of thing, to do the calculation, to calculate what the quantitative effect was for signals passing by the sun and bouncing off Mercury or Venus as they were behind the sun as viewed from the Earth, so that the signal to them would pass near the sun. And I calculated about 200 microseconds additional time delay due to the slowing effect that the gravitational field of the sun had on the speed of the waves traveling by it, the radio waves. So I figured that would be neat to measure that, but at that time, we couldn't measure the distance to better than 10 milliseconds. So to pick out an effect whose maximum at closest approach, for the rays closest approach to the sun, was 200 microseconds was hopeless. But I kept it in my mind. I even talked to several people about the idea, but I didn't write it up. But then The Haystack Observatory came into existence in the fall of 1964. And I did the calculation for it and realized that, hey, that could make the measurement accurately enough to pick out this effect. That was great. I got really excited. My first son was just about to be born. In fact, I took my wife to the hospital. At that time, men were not allowed to be present when their children were born. So I was sent home. And while my wife was in the hospital for several days, I wrote up a paper doing all the calculations up Brown for describing this effect and showing how it could be measured by radar. And that was in November of 1960, early November 64. And the paper was published at the last issue of Physical Review Letters, if you are familiar with that journal. The last issue of the year, December 28th, 1964. And I knew I had done something important because I got all sorts of letters objecting and claiming it was done first by someone else, or I had stolen it from someone else. It's amazing what it brought forth. I still have all those correspondences, but many of them, they did the calculations themselves, perhaps, but they did it wrong, so they didn't have the right answer. Anyway, so I didn't call it the Shapiro delay, of course, but Kip Thorne, who's a famous physicist from Caltech, decided to call it the Shapiro delay, and it's become the Shapiro delay ever since. And so, so how did we actually measure it? It turned out that my calculation, we could do the experiment with the then about to come online Haystack Observatory radar, turned out the transmitting power of the device that was being bought for that radar was too low to really do the experiment well, that we needed several-fold more transmitter power, and that would cost something of the order of $500,000. So I went to the director of the Lincoln Laboratory to ask him if he could get that extra money so we could get a powerful enough transmitter to do the experiment. And he said he didn't know anything about relativity, but he'd ask Ed Purcell, who was a famous Nobel Prize winning physicist at Harvard, who was very bright, very nice, and was a consultant to everybody in the country, in the military and whatnot. He's really a good guy. So the Lincoln Lab director went to him, and he said he didn't know anything about relativity either, but Shapiro has a knack for being right. And what did he mean by that? He meant he was thinking of my calculations in regard to the dipoles and the resonances, that was shown to be right, so that he then had the idea that I was usually right on such things. So on that basis, the head of Lincoln Laboratory called up his friend in the Air Force. This was near the end of December of 1960. I think, yes, 1964, before my paper actually appeared, but after it was submitted. And the guy gave him $500,000 just over the telephone, just like that, as he said, a Christmas present. So then we were off and running, and Lincoln Lab assigned a whole team of great engineers to implement the radar box, as it was called, that would do the experiment with this more powerful transmitter. And to make a long story short, it was done, and to my chagrin, it verified Einstein's prediction. I was hoping it would not verify his prediction, so the general relativity would be proven wrong, but that was not to be. So
Why did you want general relativity to be proven wrong? Briefly, that sounded interesting to me.
why? Because
Yeah.
then I'd be world famous.
Okay.
So if it's right, ho hum. But if it's wrong, that's a big deal, right?
But you got it named after you anyway, right?
Sorry?
But you got it named after you anyway.
Well, that had nothing to do with me, but it turned out to have one, so far, if you will, practical use in science. And that is the Shapiro delay is useful in determining the mass of neutron stars, pulsars. You've heard of pulsars.
Yes.
Shapiro delay gets a handle on the mass of the pulsar, and the best estimates of pulsar masses and the best limits on the high end come from the so-called Shapiro delay. Anyway, so I'm most well known for that, and most textbooks, most general relativity textbooks have a section on it.
So
Wow.
what research have you felt was most rewarding, or is there like any research that you did that we haven't discussed yet that you feel was very important to your career?
This, the time delay experiment probably made my career, if you will. I became world famous for it, even though it didn't contradict general relativity. But the next thing I got interested in was very long baseline radio interferometry, which you may or may not have ever heard of. Have you? VLBI? This was an idea that was first came into prominence in the early 1960s, where if you record the signal from some distant point object like a quasar at two radio antennas on the Earth, they will record the same signal, but one will receive it a little earlier or a little later than the other because the two antennas are at slightly different distances from this source. And then if you record those signals and cross-correlate them with one another, you can determine this difference in distance. And if you do that, well, you have to make more than one estimate, more than one observation. But the point is, if you observe several different quasars via this technique and several times during a day, you can put it all together in a complicated mathematical analysis and determine the location of the antennas, the location of the radio source, the difference in the epoch time at the two clocks that you have recording the signals at your two antennas. Of course, you can have more than two antennas, and you do these, you do all this pairwise, the cross correlations. Anyway, it's complicated in practice, but simple in principle. And it's a way of determining, among other aspects, the distances between two antennas that are arbitrarily far away from each other on the surface of the Earth. So I was then aware, because it was just coming into existence, or actually it was controversial at that time, as to whether the continents moved with respect to one another. Continental drift was then very much a subject of interest, and people were trying to measure it, and they were using his geological timescales, millions, many millions of years to determine intercontinental motion. And it occurred to me, by using this VLBI technique, we could make measurements of the distances intercontinentally to a centimeter or better over a time frame of hours, which was hugely more precise and accurate than could be done from these million-year-old or million-year timescale averages that you'd use from rocks and their magnetic orientations, which is a story in itself, which I don't have time for. But anyway, I pushed this idea of VLBI to be used for this purpose as well as to be used to measure the deflection of light predicted by general relativity. The experiment that was carried out under Arthur Eddington's auspices during total eclipse of the sun in 1919 and made Einstein a world famous figure. Anyway, this idea I had, you didn't have to wait for a total eclipse of the sun. You just had to wait for a radio source to go behind the sun, and you could do it any time of day or year that situation occurred. So I pushed this technique to be used for those two experiments. One, to measure continental drift today, so to say, and to measure the deflection of light much more accurately than was possible optically during total solar eclipses. So I try to raise money to make these geodetic measurements. And the people in Washington who had control of the money, they didn't know anything about the subject I was talking about. They had no way to judge it. Who was I? They didn't really know me. So they made the decision that, okay, this sounds interesting. Show us you can do it, and then we'll fund you. Well, that's a little awkward. It's sort of the cart before the horse in a way. But I managed in a complicated way that I won't bother you with. But it took years. And altogether, it took 18 years to convert that idea to a reliable result. But we did it. So if nothing, I was persistent. And so I am somewhat famous for that experiment as well. Then in astronomy, in trying to measure the deflection of light using this technique, VLBI, that I mentioned with radio waves, my group and I discovered so-called superluminal velocities, velocities that were greater than the speed of light. And so you might say, what? That's violation of special relativity. But no, it's not, because this was a phase effect, not a group velocity effect. I don't know if you know the difference between phase velocity and group velocity. That wave is just slightly inclined to the shore. Then if you look at the velocity at which the shores hit, you go along with the wave hits the shore in the direction perpendicular to that direction, you can get infinitely high velocities if you have an infinitely shallow angle. The closing of that angle can go very fast. You see that? But that's nothing actually is moving very fast, but so it's a phase effect rather than an actual physical effect of things moving faster. It's just the closing angle is moving faster. Anyway, I worked all that out and showed it was a phase effect, but it's not often you discover something moving 20 times the speed of light, even though it's a phase effect. And I worked out the mathematics for my group of showing how this worked. And I discovered a couple of years later that it had been worked out in Russia a couple of years before I had done it. But that was totally unknown in the West. Anyway, that was one of the contributions I made to astronomy. And I think I've said enough. I'll answer any questions.
Sure. So, what has changed working in astrophysics since you first started in the 50s? Like, obviously, a lot of questions have been answered. So, are there any other like questions that you've noticed have popped up in those years?
Or the experience of being a physicist, how like being a physicist day to day has changed, you know?
Well, there's now the standard model, which has been in place for about 40 years now, but it clearly has problems with neutrinos, which are very mysterious still, and other aspects which are very mysterious. as far as astronomy is concerned, since the 50s, the pulsars have been discovered, by Jocelyn Bell Burnell. Quasars have been discovered by Martin Schmidt. And those have drastically changed astronomy. And who knows what else has been in store. We've discovered short radio bursts that are mysterious, many of them non-repeating. So everywhere you go, we don't really understand things. Now we've opened up a whole new field in gravitational wave astronomy, where with LIGO, I don't know if you've ever heard of LIGO, they're detecting collisions of neutron stars and neutron star and black hole pairs. There are all sorts of fascinating things happening, which we're going to be able to study in greater and greater detail as time goes on, and probably discover more things, certainly learn more about the early universe, which we can probe with gravitational wave astronomy. So there's still exciting things to learn.
So what do you feel that aspiring physicists should know about working in physics that maybe people don't talk about enough, or you just discovered by working in it?
Well, I would say, if I had to give advice, that you should learn the fundamentals really well. Don't stint on that. Don't go for all these fancy things first. Understand your basic physics, that through quantum mechanics, which is very mysterious, but very rewarding and very applicable all over. In my own humble opinion, entanglement in quantum mechanics is going to be made more and more use of in quantum computers and stuff like that, which are going to come to the fore, as well as lots of other applications which haven't even been thought of yet. So I would learn the fundamentals through quantum mechanics as thoroughly as you can. Electricity and magnetism and quantum mechanics are two things I would try and learn very thoroughly. Also mechanics.
So have you experienced any particularly big challenges in your career, and how have you navigated them?
How I navigated them? The biggest challenges I've found in my career were usually political ones, having to do with raising money. But that can change. I don't have any profound insights. I always told the truth as I saw it. I was not into subterfuge, and still am not. I'm always straightforward.
I see. So is it okay if interested high school students contact you for advice and guidance via email?
Sure. I'm not all knowing in any sense. I don't have any special insights into the world. I'm not a deep thinker in those areas, but I'm happy to say what I know and say what I don't know, so to say.
Okay. Well, thank you so much for coming on. It was a very big pleasure to have you. So that was Professor Irwin Shapiro. And check out our website to see more resources about him and his work. And we'll be back with another episode.
Thank you.
Thank you. So now